Hi, everyone. Thank you for the interest in this work. My name is Jessica Mejia. I'm currently a postdoc at the University of Buffalo, but today I'm going to be sharing results from my PhD where we measured meltwater propagation through the hydraulic system of the Western Greenland Ice Sheet. Before I start, I'd like to first thank the organizers for the opportunity to talk today and to thank all my collaborators on the project. The motivation for this work is to better understand how the timing of meltwater delivery to moulins and the Moulin connected drainage system impacts ice motion. Many models that investigate the evolution of the subglacial drainage system prescribe coincident meltwater delivery to moulins throughout the entire model domain, which can exceed 100 kilometers from the ice sheet's margin in the case of Greenland. Coincident meltwater inputs mean that the subglacial drainage system should experience peak pressurization at the same time, which should in turn drive a uniform speedup across the ablation area. However, work by Hoffman and others, where they deployed GPS stations across the ablation area of Sermeq Avannarleq in West Greenland, doesn't agree with this assumption. Instead, they show that peak sliding speeds occur later in the day at their higher elevation sites further from the ice sheet's margin and earlier in the day at lower elevation sites closer to the margin. These observations indicate there are differences in the timing of peak pressurization within the subglacial drainage system that isn't currently captured by models. The application of terrestrial hydrology theory to glaciers shows us that the timing of peak meltwater delivery to moulins is controlled by catchment characteristics. An internally drained catchment refers to the area of the ice sheet surface that drains into a terminal moulin. So smaller catchments should have shorter distances to travel to reach the terminal moulin, and therefore meltwater should reach the terminal moulin faster than for larger catchments where meltwater has to travel greater distances. Work by Smith and others showed that in Greenland, the size of internally drained catchments is heterogeneous throughout the ablation area,
with lags between peak meltwater production and peak meltwater delivery to moulins, potentially ranging from less than an hour for small catchments and up to and exceeding 8 hours in very large catchments. Moreover, work by Yang and Smith shows that moulin density decreases with increasing distance from the ice sheet's margin. As moulin density decreases, catchment area increases because fewer moulins are draining a larger area of the ice sheet surface. Consequently, lags between peak melting and peak meltwater delivery to moulins should also increase with elevation and could potentially explain why peak sliding occurs later in the day at higher elevation sites, consistent with the observations by Hoffman and others.
So the focus of this work is to answer if lags between peak melting and peak meltwater delivery to moulins increase with elevation, causing peak pressures within the Moulin connected drainage system to occur later at higher elevation sites, and also determine whether the differences in the timing of peak Moulin water level can explain the later timing of peak sliding at higher elevations on the ice sheet. So to investigate this, we directly measure meltwater propagation and ice motion at 2 different elevations within the Greenland Ice Sheet's ablation area. This study is focused on the Western Greenland Ice Sheet. We deployed field camps in the ablation area of Sermeq Avannarleq in the Western Greenland Ice Sheet near Ilulissat. So let's zoom everyone in so that we can get a better look at our field site. We established 2 camps within the ablation area. We established a lower elevation site named Low Camp, and we identified a primary catchment where we could measure meltwater propagation within. We chose a catchment that had an area of approximately 0.2 kilometers squared. And this is a catchment that's pretty representative of the area with high moulin density and pretty small catchments in general. Then we established a higher elevation camp named High Camp. And we identified a catchment that had an area of over 16 square kilometers, again, representative of other catchments in the area, which were very large because of the lower Moulin density. So each camp was equipped with a weather station that we could use to monitor the timing of meltwater production. And we also used the Greenland Climate Network weather station JAR 1, which was very conveniently located between our two camps, to fill in data gaps and supplement our observations. So we also installed stream gauging stations for each of these catchments. Our gauging stations consisted of ultrasonic water level sensors mounted on a self-lowering frame that, again, would self-lower with ablation of the ice surface, giving us the distance to the water surface within the channel so that we could determine the timing of peak meltwater delivery to moulins. We also measured moulin water level by instrumenting moulins with piezometers at each camp. By instrumenting moulins and recording moulin water level, we not only were able to monitor the propagation of meltwater into the moulin, but constrain the timing of the peak pressurization within the moulin connected drainage system. Lastly, we installed several global navigation satellite system stations at each camp. This allows us to monitor ice motion so that we can determine the timing of peak sliding at each site. So, quick summary of our observations in our data set here. So we have weather station data, which we use to determine the timing of meltwater production. Stream stage gauges, which tell us the timing of peak meltwater delivery to moulins. Pressure sensors installed within the moulin to give us a time series of moulin water level variability at each site. And then we have GPS stations, which record ice motion and allow us to constrain the timing of peak sliding. So on this next slide, I am going to show you a day's worth of data that spans each of these different measurements from low camp on the left and then high camp on the right. So I am going to put on these clocks the timing of peaks across all of our observations, just to give a little bit better of an illustration of the time that all these things are occurring. And everything is going to be in local time, which is UTC -2. So first we have melt rate through time at low camp and high camp, which peaked around 115 at both locations and was coincident across our study area. The timing of peak melting was most closely related to the timing of peak incoming solar radiation, so near the timing of solar noon. Next, we have stream stage below this. At low camp, the lag between peak melting and peak meltwater delivery to our moulin was around 2.3 hours. And at high camp, we saw a much longer lag time here, with the timing of peak meltwater delivery to our moulin lagging peak melting by 6.5 plus or minus 1.8 hours at high camp. This means that peak meltwater delivery was occurring at low camp around 3:45 in the afternoon, but at high camp, it was occurring at around 7:30. So how does this affect the timing of moulin water level variability? Well, at low camp, peak moulin water level occurred 2.4 hours after peak meltwater delivery to the moulin. And at high camp, peak moulin water level occurred approximately 2 hours after peak meltwater delivery to the moulin. So this is pretty similar between the two sites and doesn't seem to vary much. But because of those that significant difference in the timing of meltwater delivery to moulins at low and high camp, peak moulin water level occurred consistently later at high camp than it did at low camp, ranging from 1 to 3.25 hours later. Here's just a really quick graph. Orange is low camp, blue is high camp, show you moulin water level with the magnitudes adjusted and plotted on top of each other. So you can see this clear phase shift in the diurnal water level variability throughout the melt season. And these were recorded coincidentally. So now to see how the timing of moulin water level and that phase shift that we just saw affects sliding speed. So at low camp, peak sliding was basically coincident with peak moulin water level as we would expect. However, at high camp, we see something different, with peak sliding occurring 2.3 plus or minus 2.6 hours after peak moulin water level was reached at high camp, which is unexpected. What this means is that at our lower elevation site, we see local controls on sliding, which we would expect, but at higher elevations, there are some non-local controls on sliding, and the timing of peak ice velocity cannot be completely explained by the timing of moulin water level and the delays in the timing of meltwater delivery to those moulins. So from our observations, we can confirm that longer delays in meltwater delivery to our high camp moulin did cause peak moulin water level to occur consistently later than at lower elevations. However, because the timing of peak sliding and peak moulin water level was not always coincident, like it was at low camp, there seemed to be some non-local controls in sliding at higher elevations, meaning our observations can't completely explain the delays in the timing of peak sliding at high camp. Now, I'll describe one potential explanation for these non-local controls on sliding at higher elevations. Okay, so how can moulin density influence hydrodynamic coupling? Basal sliding is controlled by the area integrated basal traction over an area of 3 to 8 ice thicknesses. So at lower elevations on the ice sheet, where moulin density is high, catchments are small and lags between melting and peak meltwater delivery are short. Moulin water levels should increase together, pressurizing the bed. The greater number of moulins means that meltwater is accessing the bed at more points, allowing the moulin connected drainage system to pressurize a large area of the bed, and peak sliding should coincide with peak moulin water levels, as we observe at our low camp site and how Lauren Andrews and others have also previously observed in a little bit lower on the ice sheet than our low camp site, but in the same area. So while peak sliding is occurring at low camp at our lower elevation sites, this means that meltwater is still making its way to the moulins at higher elevations, and that area is still resisting flow. In contrast, at higher elevations where moulin density is much lower, non-local controls on sliding may be explained by a higher sensitivity to other nearby catchments where peak meltwater delivery occurs even later in the day. So peak moulin water level may occur in one catchment and in nearby catchments where discharge to moulins is still ramping up. So this would mean that these areas are still resisting flow. Consequently, the timing of peak sliding may be delayed until discharge into nearby moulins increases enough to raise subglacial pressures so that these areas are no longer resisting flow. In this case, the timing of meltwater delivery to multiple catchments would need to be considered to accurately constrain the timing of diurnal velocity variability. Thank you for your attention, and let me know if you have any questions. I would like to quickly plug a talk on cryocommunity.org, which we which was developed out of the URGE program. You can scan this QR code to check out the website and look out for this talk and Q&A session on Tuesday, December 14th, 8 a.m. to 8:15 a.m. and check out this whole session for other work that's going on in the cryospheric sciences. As I said before, we have this data archived with our data, and you can contact me if you have any questions. Thanks.